Great. Thank you very much. Again, for the fifth and final time. Okay, let me briefly summarize what we talked about last lecture and where we left off. So, last time we started understanding non-perturbative corrections. By non-perturbative, I mean corrections that go like e to the minus s naught in this toy model that included topology change called JT gravity. And in order to compute partition functions of geometries that contributed genus G, we decomposed the geometry into basic building blocks. A building block that appeared in all cases was what's called a trumpet. This is a geometry that is hyperbolic. It has an asymptotic boundary of proper length beta with fixed dilaton at the boundary, and the geodesic, another geodesic boundary of length little b. That's finite. And we computed its partition function and saw that it has a different beta dependence because it has a different number of zero modes compared to the regular near horizon geometry of a black hole, which had a beta to the 3/2. In addition to that, we saw that what we could call the semi-classical piece slightly differed, and that's where the low B dependence came in. So using this shape called the trumpet, we computed one of the first basic shapes, which was a cylinder. We computed the cylinder contribution to the gravitational partition function by gluing two trumpets together using what's called the Weil-Petersen measure. Maybe it's with an I. And we saw that the mapping class group, the quotient by the mapping class group, that comes from the fact that in the gravitational path integral, we quotient by the space of largely feomorphisms of the metric, restricted our integration range for the twist variable to be from 0 to the geodesic length itself. And we were able to do this integral analytically. And if we interpret this integral as a contribution that appears in the spectral form factor, because at the end of the day, the spectral form factors compute a two-boundary quantity, and perhaps we should sum over all topologies in the bulk, what we see is that even though the leading disconnected contribution is decaying, like t to the minus 3, this t to the minus 3 came due to quantum effects in the one with determinants. Even though this part is decaying, like a power law, eventually this contribution of the cylinder that naively is subleading in power by a power of e to the s naught starts dominating at very late times, at times that scale like e to the s naught over 2. As which the spectral form factor starts growing linearly. And this is called the RAM. The thing that we didn't solve last time, and which we'll understand today, is how to understand the ramp at even later times when other geometries that are further suppressed in e to the s naught might become important. So the next question that I'll try to answer is how the heck do we compute the partition function of contributions that have arbitrary genus? The second thing that I'll try to answer is we saw yesterday as well that the two-point function of matter fields in an eternal black hole, where one operator is put on the left and one operator is put on the right, still decays even when including perturbative effects, perturbative in 1 over g Newton effect, still decays like a power law. And namely, the problem is that it still decays forever. And the question is whether there is an analogous effect like the ramp that we can see in the two-point function as well. Any questions from yesterday or from the summary?
Do you expect the ramp, or do you expect something which might constant?
No, you expect the ramp. Like if you look at a two-point function in a chaotic system, it has a very similar behavior as the spectral form factor. And I think in the first lecture, I kind of gave a qualitative argument that in system that has discrete energies, the rank and the plateau are present.
As for the ordinary spectral form factor, you have a density correlator. The two-point function case, you're just dressing that with a smooth function of energies, which encodes the OPE coefficients, but it doesn't change the correlations between nearby
Right.
energies.
Yes. Yes. So the next question is, in all these shapes, I mentioned that there's either trumpets or what are called bordered Riemann surfaces, which are hyperbolic surfaces that could have arbitrary genus. And an arbitrary number of boundaries. So the contribution of these surfaces to the gravitational path integral will denote by vol Gn of B1 for Bn. B1 for Bn are just the lengths, the geodesic lengths of the geodesic boundaries that such bordered Riemann surface has. And the question is, how do we compute this? The problem that I kind of hinted at in computing these volumes, if we knew these volumes, we can use the same gluing measure as here to glue trumpets to them, and we can compute the contribution of geometries that pretty much have any sort of topology to the gravitational path integral. But we don't know these volumes. And the problem that I hinted at yesterday is that in principle, these volumes have some moduli. They have some internal moduli that are described by the lengths of all the closed geodesics that describes them. But the problem is that in the gravitational path integral, when we have to take the quotient by the mapping class group, it's actually very difficult to make sure that we're not overcounting geometries whose moduli are seemingly different, but are related by a mapping class group transformation. So let's try to proceed very naively. This naive approach that we'll take is inspired by how people compute the partition function in 2D gauge theories at arbitrary genus. So how do you compute, let's say you have 2D Yang-Mills, and how people have computed the partition function of 2D Yang-Mills theory at arbitrary genus. This is not a far-off analogy, because in fact, this theory of 2D JT gravity can also be viewed as a gauge theory, whose gauge connection is not a compact group, but instead is the group SL2R, which is the isometry group of ADS2. But we won't use that today. The idea that people use in 2D gauge theories is to relate these volumes to volumes that either have smaller g or smaller n. So a naive thing that one might do so here I'll denote one geodesic by B, and all the other geodesics, the set of all other geodesics from B2 to Bn by big B. A naive thing that one might do is take this bordered Riemann surface, let's say this is B, and cut something that we know has a trivial moduli space. And what we know has a trivial moduli space is a pair of cans. So if you cut your geometry along the unique geodesics that are part of a certain homotopy class, then you obtain this shape as a product of a pair of pants whose lengths are B, B prime, and B double prime. And a shape that has lower genus, right? This one has genus 3, this one has genus 2, but a higher number of boundaries. And this is B. So naively, using this Weil-Petersen method that we wrote previously, perhaps we can write this, right? The gravitational path integral on this geometry as a gluing of this pair of pants to the volume of this shape. So naively, I would write something like int 1/2. So I'll put a question mark because it will turn out to be incorrect. dB prime, d tau prime, dB double prime, d tau double prime, v minus 1, b prime, b double prime, big B, minus vol, v minus 1 and plus 2 times v 0, 3, b, b prime. Now, as I said, this pair of pants is a rigid geometry. You can't, it doesn't have additional moduli rather than these free geodesics, and that's because, as I mentioned last time, in a hyperbolic geometry, there is a unique geodesic associated to each homotopy class. This shape doesn't have additional closed cycles besides the ones on the boundary, so there's no additional moduli to describe the shape. So for this reason, this guy is just equal to 1. So we've obtained a very simple formula, but even if we do a basic thing, which is try to analyze how to get genus 1 surface from an integral over a pair of pants. So a genus 1 surface can be obtained by cutting this geometry along this cycle and integrating over dB d tau, right? Or b and tau would describe the twist along that geodesic. Even if we try to do that, we obtain a divergent answer, right? Because in this case, this would be equal to integral dB d tau. The volume of 0, 3 is just 1. The integral from d tau we saw last time, its integration range would be bounded from 0 to b, and we'd obtain an integral b dB, which is over an unbounded range. So equal, bad. So what's the problem here? Are all these gravitational path integrals divergent, or are we missing something? And the thing that we're missing in this naive approach is precisely this quotient by the mapping class group. And let me explain on this shape what we're missing, and it will generalize very easily to any shape. So, yeah.
Right, in the integral, the first v factor is vg minus 1 n plus 1.
Vg minus 1 n plus 1. Yeah, sorry. I wrote 2, but it's 1. So the issue, so good. Before I mention the issue, I should just note that the same applies even if I apply, if I plug in the answer for a genus 1 surface in here and run the argument all over, I will find that absolutely all these volumes will be divergent. So the issue is that there are geometries that we're counting numerous times that are actually the same. So let's take a geometry that has for which we study two cycles, there is an infinite number of closed geodesics in different homotopy classes that can wrap these cycles in different ways. But let's just focus on two of them. Namely, we can look at a geodesic that wraps this cycle and another geodesic of length b prime that wraps am I drawing this correctly? Okay. That wraps both this cycle and this cycle once. So this is a length b prime. So this goes behind the dotted line goes behind. Great. The issue with these two shapes is that it turns out that these two geodesics are related by a Dehn twist. So a Dehn twist is the type of transformation that I actually wrote down last time. So if you guys remember, last time I wrote down that metric that included a factor of a delta function. So putting in the coefficient tau in front of the delta function to be equal to b causes a Dehn twist. A Dehn twist is just a large diffeomorphism that for which on any cycle, you choose some cycle on your geometry. Let's say I'll draw with red. And you do a 360-degree rotation of all the geodesics of all the things that intersect this cycle. So if you do that, Dehn twist, then essentially the order of these two geodesics actually flips after you do the Dehn twist. So you'll obtain a shape that has a geodesic b that of length b prime seemingly on this cycle, and another geodesic of length b. So, in other words, even though here the geodesic of length b prime and b are in different homotopy classes, a Dehn twist can relate the two geometries. Which means that these two geometries should be identified as the same in the gravitational path integral. Now, the issue when we integrate dB d tau is that geometries that have this cycle equal to length b and geometries that have this cycle equal to length b prime are always counted as completely distinct. And that's why we got a divergence. Because essentially, even though these geometries should be counted as the same in the gravitational path integral, there's a large case transformation that relates them. In this naive method that we applied, we counted them as different. Is that clear? So how do we correctly account this quotient by the mapping class group that makes sure that we're not overcounting geometries? So there's a trick that actually we'll be using multiple times today. The trick is to exchange a sum over geodesics with the quotient by the mapping class group. In other words, if somehow we find a formula in which we have to sum over all geodesics on the manifold, we saw that the mapping class group, when acting on geodesics, can move can change the homotopy class of different geodesics. So what you can do is pick a particular representative in that sum, and instead of taking the sum over all geodesics, what the mapping class group essentially does is it just leaves a single representative in that sum. So the problem is that here there's no sum over geodesics on the right hand side. So we somehow have to find a formula that expresses something that is independent of topology. In terms of a sum over all geodesics. In this case, it will be over all geodesic pairs that's together with the geodesic B, that's one of the external geodesics of these bordered Riemann surfaces, will uniquely define freehold sphere, a pair of pairs. So that together with B define a pair of pairs. Yeah.
The mapping class group is not known very explicitly as genus 2.
Uh-huh.
In order to use this trick, just knowing that you're quotienting by the mapping class group, even if you don't know how to describe it explicitly, is enough to get you to the answer.
That's right. Exactly. Even though we don't know the mapping class group, the mapping class group is a non-abelian group in general on higher and higher genus manifolds. For instance, you guys might all know the mapping class group of the torus, which is SL2Z. Here in this trick, in which we exchange the sum over geodesics with the quotient by the mapping class group, we don't actually need to know what the group is. We just need to know what generates the group. And we know what generates the group. It's the den twist around all possible cycles of the geometry. Okay, so the idea is to write a formula that roughly looks like some constant equals a sum over geodesics FB gamma, and in our case, pairs of geodesics gamma and gamma prime. Insert this somehow inside of this integral, and when taking the quotient by the mapping class group, pick a representative for each type of geometry that you end up in this sum. I'll make this a lot more explicit in a second. Okay, so how should we start? How should we find that function? And this is where what Mirzakhani did. She started constructing such a formula by taking this external boundary B, external geodesic boundary B. So let's say we have a genus 2 surface. Looks like this. And shooting perpendicular geodesics from every point on this external boundary B. So it turns out that if you shoot an geodesic into this geometry, there are three options. or actually 4 options. The first option is that this geodesic, does something complicated in the geometry, but eventually, before intersecting itself or doing anything else, it just hits one of the other boundaries of the geometry. So we'll call this option Twiddledee. So, hi. Now, the other option is that the geodesic self-intersects, and this is actually a point. We don't care what happens after it intersects, as I'll explain in a moment, but that's one of the other options. Call this A. The third option.
For the first case, you don't care whether it's the same boundary
I do. So that's the third option. That the geodesic, before it self-intersects, hits the same boundary, like here. And the fourth option, that unfortunately I won't be able to draw, is that this is called C. Let's call this A prime. Is that this geodesic goes inside of the geometry and never self-intersects and never hits one of the boundaries. It just wanders around for an infinite proper length. Just does crazy things here. And mathematicians have proven, okay, so then in principle, since roughly we can write the measure of write a measure for these perpendicular geodesics as, ranging from 0 to b, ranging over this distance, it means that I can write b as a sum of the measures that's associated for all these 4 different cases. So I'll pair up A and A prime. So formally, I have that A is equal to the measure for the type of geodesics in case A plus the type of geodesics in case B plus the type of geodesics in case C. Now, it turns out that mathematicians proved that geodesics never self-intersecting and traveling for an infinite proper length in a hyperbolic space is extremely, extremely rare. It's kind of intuitive, right? Like if you shoot something inside of a manifold, it will end up more likely in one of these cases instead of like, traveling along some ergodic trajectory that never has any self-encounters in 2 dimensions. So mu of C is equal to 0.
I think on the torus, it's completely the other way around. The generic trajectory is going to be non-self-intersecting. Because if you tilt it at a rational angle,
Rational
angles,
Sure.
And irrational angles are homothetic; they fill the space. So I would have expected,
Mu of C to be, well, I guess maybe this is the difference.
All the lines are straight. Well, on a surface, they come back. It's very hard to do this. It's very simple to
understand, but it was a surprise when you said this.
This is also the fact that it's
hyperbolic.
where all trajectories diverge from each other.
Right, but the space is compact. So,
Interacting.
okay. So the nice thing about shooting these geodesics inside is that together with the external in this case together with the external boundary, this geodesic and this external boundary, this defines a unique pair of panels on the geometry. So for instance, in this case, I already have the two boundaries of a pair of pans, and a third boundary can be obtained by choosing the geodesic that's again unique and is homotopic to the union between this cycle, namely this geodesic. Here, if I thicken the external boundary, and I also thicken the geodesic that I've drawn, and I make these lines thicker and thicker, I again end up defining a unique pair of pans. I can choose the geodesic that's homotopic to this cycle. So starting from the intersection point and going back to the intersection point, that defines a homotopy class. And geodesic that looks like this. So these three geodesics define a pair of pans that's unique, associated for each geodesic that's sent perpendicular to the boundary in this case. Same here. Namely, if I thicken these lines, there's a geodesic that's homotopic to the cycle starting here and ending here. So, homotopic to this plus this plus this plus this. The point is that these cases, each one of these cases, can in turn be split into a measure associated to geodesics that are associated in turn to a unique pair of pans defined on this entire geometry. So, for instance, mu of A, mu of B, that was this case. It's a sum over geodesics that define different pairs of pans. The different pairs of pans have one external geodesic that I'll label by I. That's in the set B of all other external geodesics, and another geodesic gamma. Sorry, another geodesic lambda that ends up defining a pair of pans. Here by epsilon I denote the all possible pairs of pans that have one external boundary and one internal geodesic boundary of some measure mu that's defined on bi of gamma. And similarly, mu A is defined as a sum over all possible pairs of pans that have both boundaries being internal, just like in this case. Here, both the red line and the orange line are internal. plus cases in which this geodesic, well, I didn't explicitly draw one here, but there's clearly cases in which this geodesic defines a pair of pants where one of the geodesics is external. Let me just quickly draw a case. For instance, sending this, shooting this geodesic that comes back to this boundary, defines this pair of pants. That's in the case A, where one of the geodesics is external. So sum over I and B, lambda and epsilon I, mu A I lambda. So essentially, there's these two types of pairs of pants. One that has an external, one that has an external geodesic as part of the pair of pants, in addition to the external geodesic of length little b, and one that has the other two geodesics as internal geodesics in my manifold. And in turn, these cases can be further separated depending on how the geometry ends up looking if I cut my geometry further along all the geodesics of the pair of pants. So let me just draw some examples. So I can end up with a geometry that's connected after cutting a pair of pants out of the geometry. So the resulting geometry is a pair of pants plus something connected that has lower genus, right? I started with a manifold of genus 2, and I ended up with a manifold of genus 1, but free boundaries. Or I could end up with shapes that are lower genus and disconnected. For instance, I have pairs of pants that look like this. Or I can have a pair of pants where one of the boundaries is external, and the geometry that I obtain from this cut is always a connected geometry because it only has one. So these are the possible cases when the pair of pants is part of epsilon, and these are the possible cases when the pair of pants is part of epsilon I. Here, notice that the resulting boundary that I obtain after the cut doesn't have lower genus, but it has a lower number of external boundaries.
Sorry, what was capital lambda again?
So lambda, capital lambda, denotes the set of pairs of pants. The pairs of pants on this manifold are two types, so they always involve the geodesic B, right? Because that's where I'm throwing my orthogonal, my geodesics that are orthogonal inside of what, that's where I'm shooting my geodesics from. And they either consist of two other geodesic boundaries that are internal, or a geodesic boundary that's internal and one that's external.
So if I, and so that geodesic attaches somewhere on B. Is it imagined that there's some kind of cell decomposition you get when you sort of slide the endpoint along the boundary B?
Here?
Yeah. So that geodesic is attaching somewhere, right?
Yeah, so it's attached here,
right?
And it shoots.
So presumably you get an open set in the moduli space if I move the endpoint a little bit?
Yes. Yes,
So,
if you move the endpoint a little bit, probably this geodesic will still stay inside of this pair of pins.
Right, so if I keep sliding it along, then presumably at some point I hit one of these other.
Exactly.
So in that way, do I get some type of cell decomposition?
Yeah, you get a decomposition into all these types of geometries. You get these three possible cases. Well, two cases when lambda is in upsilon, and a single case when lambda is in upsilon I.
But presumably, if I keep sliding it along, at some point I hit one in case C.
Right, but the point is, if you keep sliding along, you will hit the case C. But if you move it an infinitesimal amount, you'll get out of case C and back to one of these cases. I don't know exactly how the proof goes for proving that mu of C is equal to 0. That's something I took at face value, but I can send you the reference if you want. So the nice thing is that you can now kind of intuitively see that these measures mu A of gamma, mu A of lambda. Mu A of lambda, mu A I of lambda, and mu BI of lambda only depend on properties of this freehold sphere, because the geodesics that defines these three different sets are completely contained within each pair of cams that defines this set. So in other words, since a freehold sphere is only defined by three parameters, these three measures only depend on B, the external geodesic length, B prime, and B double prime, where B prime and B double prime are the other two geodesic lengths involved in this freehold sphere. In this particular case, either one of B prime or B double prime might be equal to one of the external geodesic lengths BI. So in other words, I now obtain a formula which writes B, the measure over all geodesics that are perpendicular to this external boundary, that writes B as a sum over all pairs of cams on the manifold, some that only involve internal geodesics, and some that involve external geodesics, a single external geodesic, of some measure that I'll call B. For this case, mu, for the case where one of the boundaries is internal, plus T. For the case when one of the boundaries is external, plus B. So this just uses the fact that these free measures can be written only as a function of the free geodesic lengths that define the freehold sphere. So this is exactly the type of formula that I was looking for, because it expresses something that's independent of the topology of the manifold, namely the length of an external geodesic, as a complicated sum over all pairs of cams on my geometry. Now, this T and D actually turn out to be related to the length of the geodesics that I shoot inside of this pair of cams. So it's related to geodesic length. So it's related to the length of the gamma that defines lambda. And people have computed them explicitly because they know, essentially, they can compute explicitly what's the length of all these geodesics that you shoot in on a pair of pans. So for instance, T, B, B prime, B double prime, it's the log cosh B double prime plus cosh prime plus, sorry, B plus B prime over 2 divided by cosh B double prime over 2 plus cosh B minus B prime over 2. And the D can be determined by looking at the special case in which I write down this formula for the pair of pans itself. So for the pair of pans itself, upsilon is unique. It's the pair of pans itself. So B can also be written as a sum between D, B, B prime, B double prime, plus T, B, B prime, B double prime, plus T, B, B double prime, B prime, which determines D. So now you get this funny formula where you essentially write an external geodesic length as a sum of like very explicit functions that you know of a sum that involves all possible pairs of pans that you can write down on this hyperbolic geometry. So now let's revisit the decomposition that we were talking about earlier. Namely, instead of writing B, n plus 1, B, E, as an integral involving a unique pair of pans, let's multiply this by some constant B that's involved on the left-hand side of this equation. And then write B as a sum over all possible pairs of pans on the geometry. And then cut out those pairs of pans to see what manifolds I'm left over with. Now, after taking the quotient by the mapping class group, essentially this sum over all possible pairs of pans reduces to a single representative in that sum. By a representative, I mean that we can define pairs of pans that are related by the action of the mapping class group on the two external geodesics. In this case, the two geodesics that are the internal geodesics of the manifold. And in this case, the one geodesic that's written in this case, that's one of the internal geodesics of the manifold. Using that, exchanging essentially the sum over geodesics by the mapping class group, we end up with the following. B times V is 1/2 times an integral from 0 to infinity dB, an integral, B prime, an integral from 0 to B prime, B tau prime, an integral from 0 to infinity dB double prime, integral from 0 to B double prime, B tau double prime. And I have geometries that were obtained from the case A or B, where both the geodesics the other two geodesics of the pair of pans are always internal. So it's this times Bg minus 1, B prime, B double prime, B. So this, you could think about the case in which we had our manifold found a freehold sphere and cut our manifold into a piece that had genus G minus 1 and a single connected component, plus a sum over all possible disconnected components of V H1 V prime, V1, V H2, V double prime, V2. Here, H1 plus H2 is equal to the genus G, and V1 union V2 is equal to all the external manifolds V. So this looks something like breaking the geometry into a pair of hands that separates the space-time into two disconnected components, one of genus H1 and one of genus H2. So this is analogous to this case. And then finally, I have the cases in which one of the geodesics of the pair of hands is external. So this corresponds to taking sum over all possible geodesics that are external. For the lengthy formula. So essentially, this volume corresponds to separating my geometry into a pair of hands that has B as one of the external geodesics, another BK as the other external geodesic, B prime as the junction geodesic, and then the surface of genus G as the manifold that I separate. So this essentially is the generalization of this case. Great. So the property, again, that I used here is that I inserted this formula into the integral of over all possible cuts over a pair of hands and some internal manifold. And then when taking the quotient by the mapping class group, I just chose a representative pair of geodesics that ends up defining these three possible cases. In other words, if I acted with any twist on these two geodesics, in this case, this has length B prime and B double prime, I would always obtain a type of geometry that after cutting along the two new geodesics always has this sort of cut into a pair of hands and a geometry of genus G minus 1. So that's why essentially these are the three representative cases. So this formula seems super abstract, but essentially what it provides, these formulas for D are known. I wrote them above for what T is, and D can be easily determined from this case. And it always involves, on the right-hand side, geometries that either have lower genus or either have a smaller number of boundaries. So it's essentially like a recursion. So let's revisit the simplest case that failed before for reproducing what the moduli space volume of a surface that has genus 1 is. So previously we were looking at this shape,
Can I just ask a stupid question? So,
Oh, yeah, go ahead.
with the den twist, the seems representative, if I do with a den twist, it does mean that I go from, I stay in the same class?
Yes, yes, yes. So when you do a den twist, you always stay within the same class.
So you separated your expression into den twist invariant parts and
Exactly, and you can always prove that essentially pairs of pans that are how should I say this? That all pairs of pans that are part of this class have internal geodesics that can be related to each other by den twists. So the different cases, if I take one case, let's call it lambda inside of upsilon, and another case lambda prime also inside of upsilon, and lambda prime after I cut my manifold along these two geodesics, I obtain the same time of cut either in this category, or this category. So if lambda and lambda prime have the same time of cut, then you can prove that the two are related by the action of the mapping class group. So that's why you only have to keep one of them. And it's kind of clear that a case in this category and the case in this category cannot be related by the mapping class group because there's no possible large diffeomorphism that would change what topologies I get after I cut along a certain geodesic. Okay, so let's go back to this case.
Are you somehow selecting some representative where the geodesic you're shooting out has a minimum length under all the geodesics that are related by date twists?
No, it's I'm essentially I would have this formula with an integral over dB dτ and a sum over all possible pairs of pans. And the point is simply that let's see how to say it. Like suppose that you have sum over f of g acting on h, where g is consists of all group elements of some discrete group Perley G. Then if I want to essentially gauge the action of G, I can just choose. Maybe I should find a better example. No, I'm just picking a unique representative in the class that's just defined by the type of topology that I get after the cut. Using the fact that all lambdas and lambda primes that are part of upsilon that look the same after a cut are related by the mapping class group. So that if I quotient by the mapping class group, I'm just left with one of these cases. Does that make sense? Okay.
Can I equivalently think that your measures D and T take into account these kind of overcounting and
Sorry?
does the D and T measures take into account this overcounting? And is this where the mapping class group come into impact here?
Yeah, so the D and T appeared in that sum, right? Overall possible geodesics. So that's a statement that's true on any hyperbolic manifold and has nothing to do with the mapping class group. But then when I take the quotient, essentially instead of summing over all possible pairs of pans, I just choose a representative, and you use the fact that the dB dt, this measure, is invariant under the action of the mapping class group.
I think maybe what I'm puzzled by is that somehow, somewhere in some step along the way here, so you started off by talking about shooting out geodesics perpendicular to the boundary and following where they go.
Uh-huh.
And then at some point, you stop talking about those geodesics and just are talking about the lengths of boundary geodesics themselves.
Yes,
And
because
when you're doing pairs of pants.
uh-huh.
So where along the way did you lose because the setting up those perpendicular geodesics from the boundary, that's the kind of thing that's not invariant under the Matlin class. Because you make a Dane twist, you wind up that geodesic in some complicated way on the Riemann surface.
Yes.
So somehow.
Well, the first statement applied to any hyperbolic geometry, and it didn't have anything to do with gravity or the mapping class group, right? It was just a statement that the measure over all geodesics that are perpendicular to the boundary can just be related to that complicated sum that only depended on B prime, and B double prime. And essentially where I went from shooting in geodesics to talking about pairs of pans was through the fact that a geodesic that's perpendicular to the boundary that was in the class A or B uniquely defines a pair of pans. And the measure over that specific type of geodesic that I encounter is also just determined in terms of the properties of that pair of pans that it defines. So it's only determined in terms of the geodesics B prime, and B double prime. Does that answer your question?
Yeah, I think so.
So that was the transition step. It was, I think the important thing is that the important observation is that these perpendicular geodesics that are perpendicular to the boundary can be used to uniquely define pair of pans that decompose your manifold into essentially a sum over all possible pairs of pans that belong to that can be written down on that geometry. Yes?
Does the size or the volume of this pair of pans matter? Are we?
So let me think for a second. The volume of a pair of pans is actually always the same due to Gauss-Bonnet's theorem. It's a kind of a non-intuitive thing. I think that's true. Yeah, because half integral of R plus integral of R plus half integral of K is 4 pi times the Euler characteristic. Is it 4 pi or 2 pi? Anyway, either 4 pi or 2 pi. Integral of K for a pair of pans is always 0 on each one of the boundaries because K is 0. They're geodesic, so this is 0. The scalar Ricci curvature on the geometry is always constant. So R is -2. So a pair of pans has 3 boundaries. So the Euler characteristic is -1. So you obtain integral of -2 square root of G is equal to -4 pi. So area for volume equals to 4 pi. So it's always the same. But what was important was that the measure, right, that mu A lambda depended on B prime, and B double prime. So it depended on the parameters of the pairs of pans.
Yeah, okay.
So in some sense, yes, you are right that it depends on the parameters of pairs of pans, but not on the area because the area is always the same.
Yeah. Okay. No, I was wondering, wouldn't we care about the length of the internal geodesics, but
internal where?
internal geodesics inside a pair of pans, right? I mean,
There are no other internal geodesics inside of pair of pans.
Yeah, but when you're shooting these perpendicular geodesics, right, they will have different lengths.
Yes, and that's exactly how people determined what these functions are.
Oh.
I won't go through the derivation because it's a bit complicated, but they use the length of the geodesics to determine those functions.
Oh, that's how it goes in. Okay.
Okay, so let's do the simplest, the concrete example. This formula that looks really ugly simplifies a lot in this case because there's only one possible case that one can encounter when decomposing these genus 1 surface into a pair of pans. Namely, it's the case in which I can write this as an integral from 0 to infinity dE prime, an integral from 0 to b tau prime, b prime, b prime, times a pair of pans that has 1b prime, and 1b prime here. So the difference between what we wrote previously and the correct formula is precisely this measure factor d of b prime that appeared through this trick of rewriting this term b as an infinite sum over all pair of Pans decompositions of this genus 1 surface. So the volume of this guy, as I said earlier, vol 0 free of b prime is equal to 1. There's a unique pair of Pans with these lengths, which means that v11 of b 1 over 2b integral from 0 to infinity b db b prime db prime b prime. So using the formula, the explicit formula that one had for db b prime, which was related to the formula for t, for that measure t, it turns out that this can be evaluated explicitly, and one just obtains that it's b squared plus 4 pi squared over 48. So essentially from nothing, from a formula that seemed like a trivial, well, a complicated, but a formula that seemed to have nothing to do with gravity on a hyperbolic surfaces, we managed to obtain one volume. And by using these volumes together with the fact that V0 free is equal to 1, we can essentially recover any possible volume with any possible genus and any number of boundaries. Because as I said, this is like a recursion relation. So we start from something like this and just keep plugging back into that formula. So with this, let's compute the leading order non-perturbative, the first non-perturbative correction to the disk JT partition function. So the partition function with a single boundary. So essentially, I can take this shape and glue it along this external geodesic to a trumpet. So the partition function at genus 1 is just given by the e to the minus s naught. The Euler characteristic of a genus 1 manifold is e to the minus s naught. Sorry, gives a power of e to the minus s naught. That's a function of e to the minus s naught. BDB, the trumpet of beta b. B11 b. I now know what B11 is. It's just this polynomial. And you can do this integral explicitly. I know what the trumpet is. I know this polynomial. The trumpet is just a Gaussian function in the parameter little b. So doing a Gaussian function times a polynomial is really easy. And you just get this b to the power 3/2. 24. So it's m breaking times b to the power 3/2, 24 square root of pi, plus pi to the 3/2, breaking m beta to the power 1/2, divided by 12 times square root of 2, times the factor of e to the minus s naught. So now I have to add this if I want to obtain the partition function coming from surfaces that have a single boundary. So z of theta, the graph of theta, which was z corresponding to a disk, so z01 of theta plus z11 of theta. So surfaces with genus 1, like this one, plus dot dot dot. That's up leading in e to the s naught. This, we computed this yesterday. This went like, or 2 days ago, this went like e to the s naught times b to the minus 3/2 at very low beta. So here I'm gonna look at what happens when beta goes to infinity. Plus e to the minus s naught b times m break to the plus 3/2 times order 1 numbers. So why I wrote this formula, and why I thought it was interesting, is because notice that as the temperature becomes very low, eventually this non-perturbative correction kicks in and dominates over the contribution coming from genus 0. So namely, when beta becomes of order e to the 2 s naught over 3, geometry with wormhole dominates. And morally, this is related to the comment that I made in the one of the first days, that essentially when we do the perturbative computation in 1 over g Newton, the regime of validity for that computation is up to temperatures that are non-perturbatively small in e to the s naught. So here I write things in terms of temperature. This is valid up to e to the minus 2 s naught over 3. And here we see an example of a type of non-perturbative correction that ruins that, or not ruins, that gives a correction precisely at the estimated scale for the breakdown of the regime of validity. And if you want, this blow-up is somewhat natural because at the end of the day, we expect that if we take the literal beta going to infinity limit of a partition function, we'll obtain that the partition function is equal to 1 if the ground state energy is normalized to be 0. While this leading term seems to give us that the partition function goes to 0 as beta goes to infinity.
What's the sense of a temperature of order this scale? I mean, the gap, so we're talking about like supersymmetric black holes. The gap is enormously huger than this.
Yeah. So this is for non-supersymmetric.
Okay.
Yeah, so here there's a sense because the density of states seemingly goes all the way to these temperatures. And, you know, this makes perfect sense as a question in field theory.
Okay,
we can look at a sector of fixed charge in a field theory and ask what happens if I scale the temperature with e to the with the number of states.
So for non-supersymmetric systems, this scale e to the s naught is basic. Is the gap to the first excited state?
Basically, yeah. E to the minus s naught is like the gap to the, it's m break times e to the minus s naught is the gap to the first excited state. So it's super tiny. Okay, maybe let's take a break. Let's restart. So we left off by computing the leading order correction to the gravitational partition function with a single boundary, and saw that as the temperature became non-perturbatively small, or the inverse temperature non-perturbatively large, these wormhole geometries can start dominating. So more generally, to compute z graph of beta 1 for beta n, I just, yeah, sorry.
In terms of the density of states, these genus 1 corrections to the Schwarzian,
Yeah.
what do they look like? Are they still exponential in the energy?
Like now.
The first term, gives you the Schwarzian.
Yeah.
So is genus one correction?
Yeah, I think they need to blow up. Yeah, they need to blow up as the energy goes to zero in order for this power to be beta to the 3 halves, right? So the reason why this went like beta to the minus 3 halves was because the inverse Laplace transform of beta to the minus 3 halves is for the B. Just like here, the inverse Laplace transform. Okay, I won't embarrass myself computing the inverse Laplace transform of that function, but it blows up, right?
Does it grow also at large E? Like the
No, it does not grow at large E, and that's related to the fact that the trumpet density of state. So if you Laplace transform the beta for the trumpet, I think that goes like a cosine. So essentially, the answer to your question is that you have to do an integral between a cosine and a polynomial. And I think you'll get some oscillating, I imagine you'll get some oscillating trigonometric function in the energy at your density of states. That probably blows up as the energy goes towards zero.
To follow up the question I asked before the break, so if we redid this for supersymmetric systems, would the
I will make a comment at the end about supersymmetric systems.
okay.
The answer
Is this torus modification just irrelevant?
it's zero as beta goes to zero, beta goes to infinity.
Okay.
And you can prove that very explicitly.
Is that
All
something
higher.
zero mode appearing or something?
It's a bit more subtle than that. In the case of a supersymmetric index, if you compute a supersymmetric index instead of a partition function, it is due to an extra zero mode appearing. In other cases, it's a bit more subtle. But you still get that as beta goes to infinity, all these other contributions are zero, with the only exception, so you could also allow defects to proliferate through your geometry, and that's what their contribution is. Their contribution is also zero, except for defects that preserve supersymmetry, and there's only one type of defect that preserves supersymmetry in the supersymmetry case. But essentially, the answer for the ground state degeneracy is just given by the black hole geometry plus a type of orbifold of the black hole geometry. And this resonates with a number of results that people have obtained from rewriting the string theory answer for the BPS count of black holes. So, for instance, this resonates with the fairy tale story and the fairy tale expansion and so on. All right, so to obtain Z gravitational with an arbitrary number of boundaries, I was asked during the break, you simply just have to do the same integral over n trumpets. This time, each integral is a Gaussian. And the account for some overall genus of these volumes that now have n boundaries, B1 for Bn. And perhaps one thing that was not at all obvious, but it is actually the case from the formula that I wrote down, was that if you plug in these volumes in the recursion relation and obtain them at higher and higher orders, you will always find that these volumes are just polynomials in all the BIs. Good. So I forgot an e to the s naught minus e to the s naught times the Euler characteristic at genus G and then boundaries. Okay. So we've managed, in some sense, to do the gravitational path integral in this toy model to all orders in the e to the s naught expansion. But there is some slight interpretational problems. Namely, as you can see from the above formula, well, as you can probably imagine, these multi-boundary quantities are non-zero. And it's a bit unclear what that means. Well, we computed one case explicitly, the case of the cylinder. it's a bit unclear what the fact that they're non-zero means from the perspective in which these black holes are supposed to be equivalent to conventional quantum mechanical systems. So, first, how should we interpret this? Since the gravitational partition function with boundaries of renormalized lengths beta 1 and beta 2 is different than the gravitational partition function with boundary of length beta 1 times the gravitational partition function with boundary of length beta 2. And this is known as the factorization puzzle. And it not only persists in this model, but it also exists in higher versions of ADS-CFT. And in this model, at least, a resolution to this puzzle is that instead of the black hole being dual to a conventional, instead of black holes in these two-dimensional theory being dual to a conventional quantum mechanical system, it's dual to an ensemble. So from conventional, we consider an ensemble. So, and as we shall see, the recursion relation that we wrote down for these volumes will make it actually very precise what type of ensemble we have to consider. The proposal is that to write, if I consider an ensemble of theories, then the n-boundary partition function is an integral over all possible Hamiltonians of this ensemble, with a measure over Hamiltonians times a trace associated to each insertion of one of these boundaries. And the specific measure over Hamiltonians that turns out to be the correct measure for the toy model that we're discussing is a measure that typically people encounter in matrix integrals. Namely, if you take this probability over Hamiltonians to be given by e to the minus L trace of some potential v of h. And this measure over integration measure over Hamiltonians is given by the van der Waals measure. So here L, H, we'll start as thinking about them as L times L Hermitian matrices. And these types of integrals are widely studied in matrix models. When people study matrix models, this is exactly the kind of stuff that they study. And the type of observables that they like to insert in addition to this trace of e to the minus beta h, which I'll just denote by z of beta. So we should distinguish z grav from z of beta. So in addition to that, other useful quantities that you can insert are what are called the resolvent, which is a trace of 1 over e minus h, or the density of states itself, which is a sum in each member of the ensemble of delta functions that only have support at the eigenvalues of h. So all these quantities can be used essentially to study the eigenvalue statistics for the matrices H. So the proposal is that there is a specific limit of a matrix model for which Z in the matrix model agrees. So this is an ensemble average of insertions of Z of beta 1 to Z of beta n. Z in the matrix model, beta 1 for beta n, agrees with Z gravitational beta 1 for beta n. Now, in matrix models, it's typical that all these expectation values, whether it be expectation values for resolvents or expectation values for partition functions, admit what's called a genus expansion as well. In which Z can be written as a sum over G from 0 to infinity, Z, G, n, E1 through Bn, L to the 2G plus n minus 2. And this can be obtained by literally doing the equivalent of Feynman diagrams in when expanding around the saddle point of this integral for large L. However, and the typical example that most of you might have already encountered for matrix integrals are Gaussian matrix integrals, whose density of states at leading order is what's known as Wigner's semicircle distribution, where energies range, well, depending on some normalization, can range from 0 to A. Typically, we say that the eigenvalues in a Gaussian matrix model range from -A to +A or -1 to +1. But here we can just shift the ground state energy. But the important thing is that the shape of this density of states, the shape of this density of states that measures the density of eigenvalues of a random matrix H is a semicircle. And more generally, changing the potential V of H can give you different shapes for this density of states. The universal aspect that is already tantalizing is that the density of states, the leading density of states as it approaches one of the edges, goes like square root of E. So even if I change the potential, as long as I keep P of H to be e to the minus L trace V of H, I still keep the square root of edge, but I can change the overall edge of this potential. So that's this plot already brings up a problem with the proposal that I just mentioned, because we just computed the leading density of states in JP gravity a couple of lectures ago and saw that the energy ranged from 0 to infinity, not over a finite range as these typical matrix models seem to suggest. So here ranges from it has some range, let's say from A minus to A plus. Here I just chose A minus to be 0. While for our black holes, P range from 0 to infinity. And this is resolved by something that's called the double scaling limit. In which tuning A, so A can also be viewed as one of the parameters of the potential. We can tune A plus minus A minus, we call this A, to go to infinity, while at the same time taking L, the size of the matrix, to go to infinity, while keeping 8L over I to the times A to the 3/2. This we'll call A to the S naught to be fixed and finite. So finite at large. So in this expansion, this is called the double scaling limit. And in this expansion, e to the s naught controls the eigenvalue density. As Emil said earlier, the spacing between eigenvalues is of order e to the minus s naught. This is precisely what happens in this double scaling limit. So e to the minus s naught is the typical spacing. So, for instance, here, doing this double scaling limit for the Gaussian matrix model leads to what's called the Airy model, which has a density of states that still has a square root edge, but the square root edge goes all the way out to infinity. So, well, V. Good. While in what we'll be working on, we'll be choosing some potential for our matrix integral in such a way that at leading order, it reproduces the potential that we got from the disk computation in JT that at low energies also had a square root edge, because sinh of 2 pi square root e goes like square root e in the low energy limit, but at large energies it's exponential in e.
So which one's the area model? The white?
Oh, white is airy. It's the double scaling limit of white. And red is JT, because it's the double scaling limit of red. Fantastic. And the nice thing in this double scaling limit is that instead of having an expansion in L for all observables, just like I had here, I instead have an expansion in e to the s naught that has finite coefficients. Okay, so this already starts looking a little bit like the JT expansion. The question is, can we get these ZGNs to match with the ZGNs that we obtained from the gravitational path integral? And the starting point for that.
So there is a rescaling of A, right? Over there, you cannot just change. Did you just flip L and e to the power of s? In the
Yeah, so the point is that these ZGNs also depend on A.
Yeah.
And after doing the double scaling limit and taking this precise definition of e to the s naught, you can rewrite this as an expansion of e to the s naught. It's a bit non-trivial to understand why this particular power of A, well, not that non-trivial, but okay, this specific power of A causes the expansion after taking the double scaling limit to still be well defined and have finite coefficients. The other thing that you have to know about a matrix integral is that V, the form of the potential V of H, uniquely determines, and vice versa, the form of the leading density of states, rho 0. So essentially, if I input a leading density of states, rho 0, I can completely determine the potential V of H. And in turn, that means, since the potential is determined, that means I'm essentially determining what theory I'm talking about. Which means that in turn, I can determine all these coefficients ZGN using matrix integral techniques. And I'm gonna speed this up a little bit because you guys have the resource of the lecture that you had in the fall from your colleague here, Einard. The idea is that if you choose rho 0 of E to be precisely sinh of 2 pi square root of V divided by m break, this determines something that's called the spectral curve of the matrix integral. Which is simply, this is little set sine of 2 pi square root of m break times z divided by pi. Let me just write it down fully. Actually, m break inverse, m break inverse. And from the spectral curve of the matrix integral, it turns out you could actually write down a recursion relation for all the expectation values of z and the expectation value of many other observables in the matrix integral, such as the resolvent. And in particular, there is a quantity that's related to the resolvent. So the resolvent itself has a genus expansion. And it's convenient to reparameterize the resolvent in terms of squared variables. Just like here, notice that in the spectral curve is essentially related to the leading density of states for a transformation in which E goes like minus D squared. So if we reparameterize the resolvent in terms of this function, omega, that has additional factors of Z, it turns out that W, sorry, not omega, but W, Gn, satisfies a recursion relation that's equivalent to the recursion relation that I wrote previously for the quantity V, where the quantity V from the matrix integral perspective is defined such that WGN is the Laplace transform of V. So 0 to infinity, bi dbi to the minus square root of 2 m break inverse bi zi vol gn of bi. So the recursion relation that people derived in matrix integrals for WGN implies that the inverse Laplace transform of these W's, it's a roughly an inverse Laplace transform of these W's, also satisfy a recursion relation. And one can prove that the recursion relation satisfied by these quantities that I also called V is precisely the same recursion relation that Mirzakhani wrote and that I sketched out, whose derivation I kind of sketched out before the break.
Is that recursion relation the same or different from the sorts of recursion relations that people used to write down for matrix models?
This is the same. The same type of the recursion relation that this guy satisfies is very simple. It doesn't involve any integrals. the integrals that you saw in the integrals over little b that you saw in the previous recursion relation for the volumes are there because when going from these w's to these v's, we have to do these integral transforms. So you might be accustomed to the recursion relation that doesn't involve these integrals over dB.
Right.
But the reason why we have these additional integrals is because of this transform.
And so, so is there some intuition as to this particular matrix potential? So the Gaussian matrix model is already understood to be topological gravity, all sorts of topological recursion relation. Modifying it from being square root forever to being sinh square root, I mean, is that?
I think this just corresponds to this specific gravitational theory. In principle, we can also modify the sinh of 2 pi square root of e by changing the dilaton potential in gravity. So that changes the density of states. And one can write genus expansion in that case as well.
Is that map understood?
Yes, and it turns out that the recursion relation that those partition functions satisfy agree with the recursion relation in a matrix integral with a different potential defined in such a way that that potential gives you a leading density of states that agrees with the gravitational answer.
And it so there's some dilaton potential, you call it, I think, u of phi.
Yeah.
Is the explicit map between u of phi and v of h understood?
Roughly, yes. Yes, I think there are analytic formulas. If you give me a u of phi, I can give you what v of h is. You know, the complicated formula. It also depends a bit on how you take the double scaling limit, but I think it's well, I think it's essentially been done. Okay. So this.
One more.
Yeah, please.
So also back in the day, people understood various non-perturbative effects as being related to individual eigenvalues of matrices. So, as being various e to the minus. I guess e to the minus. There was effects that were exponentially small in
L.
e to the minus n. E to the minus L effects, yes.
Yeah, so these would be e to the minus e to the s naught effects. These are we can call them doubly non-perturbative effects in 1 over g Newton because that's not goes like 1 over g Newton. And I will actually talk about them now.
Okay.
I will not derive how people obtain doubly non-perturbative effects, but. Okay, actually, one reason why it's important to talk about what Emil mentioned, which are doubly non-perturbative effects, comes from the following reason, which is that this expansion, it's a bit difficult to prove this, but the expansion, the genus expansion, both on the matrix integral side and on the gravity side, okay, they're equivalent, but they're both asymptotic expansions in e to the s naught, meaning that these coefficients GGN grow faster than g factorial. And that's a consequence of that comes from the growth of the coefficient of the polynomials in the volume turn out also to grow really quickly with g. So that's why these expansions turn out to be asymptotic. And whenever we encounter asymptotic expansions, it's important to talk about non-perturbative effects in that expansion, which in this case, our expansion is in e to the s naught. So this will lead to effects that are suppressed like e to the minus e to the s naught. And such effects are particularly important for a quantity that we talked about earlier, which was the spectral form factor. So
So I can ask a very simple
Yeah.
question. What is the scale in which you consider M breaking? Because here I suppose you take the dimensionless in the matrix model.
Oh, no, it's, I think dimension full. We can say that these eigenvalues, you know, it's Hamiltonian, it has dimension of energy. So it's eigenvalues of dimension of energy.
Okay, so then Z has just square root of energy. Oh, sorry.
Z?
So in the spectral curve, right, you have, what are the,
Well, so the density of states has dimension of inverse energy, and the spectral curve is defined with respect to the density of states. So it has roughly the same dimensions as the density of states. I think what Anord and Marathan did was absorb this factor of M break in the definition of Z. So I think they wrote this. But if you want to keep this scale as giving you where the cinch kind of curves down, then it's actually good to put this additional numerical factor in the spectral curve as well that defines the matrix integral.
so I also thought that was a plus, which confused.
With M break plus 1.
Yeah, no, I thought it was like M break plus sin. So that, yeah. So I'm confused. No, sorry.
Sorry, no. It was a product.
Thank you.
Okay. So as I said, at this point we've established the relation that all genus expansion of the matrix integral agrees with the all genus expansion of the gravitational path integral. But in principle, this expansion is asymptotic, but the matrix integral provides us with tools to understand contributions that are non-perturbative, that kind of non-perturbative in e to the minus s naught, that kind of help us make sense of these asymptotic series. So let's see how this happens for the spectral form factor. So it's convenient to rewrite the spectral form factor, which we now can view as an ensemble average of two copies of a partition function over P of H in terms of an integral over energies times the correlator of two densities of states. Now, the reason why this is convenient is because this correlator of densities of states, as Jorrit also mentioned in his seminar yesterday, is one of the most universal quantities that we encounter in matrix integrals. Namely, as the two energies approach each other, eigenvalue repulsion effects that are famous in matrix integrals become important in this correlator. So the reason why we care about the regime when eigenvalues approach each other is because the spectral form factor at late times is dominated by if I make T very large, it's dominated by contributions for which E and E prime are very close to each other, right? I'm taking the Laplace transform with an extremely large coefficient. So I care about the limit in which E goes to E prime. So rho of E prime, from the matrix integral point of view, it has been shown that it takes the following universal form as E approaches E prime. By E approaches E prime, I don't mean that E minus E prime is of order E to the minus S naught. I actually just mean that E minus E prime is much smaller than M break. So it contains a disconnected piece. It contains a contact term. And in addition to that, it contains a piece that we calculated yesterday that corresponds to the cylinder contribution that turns out to be universal and independent of the density of states, as some of you observed yesterday. So because it was independent of membrane, that contribution goes like in the row correlators, instead of z goes like 1 over 2 pi squared e minus e prime squared. And in addition to that, if you sum all geometry and do the resummation of the asymptotic series, in principle, you get another piece, which is a highly oscillatory piece, but again, is universal, that goes like 2 pi rho 0 of E bar. So this is E bar times E minus E prime divided by pi squared E minus E prime squared. So here rho 0 of E is e to the s naught times rho disk. And if I define the rho disk to be independent of s naught, then rho 0 scales like e to the s naught. So essentially, this is the leading piece. If I view this as an e to the s naught expansion, this is the leading piece, right? Because it goes like e to the 2s naught. This contact term seems subleading because it goes like e to the s naught. This piece goes like order 1. And that's what the wormhole contribution was that we discovered yesterday. And this piece, notice that it goes like the cosine is like an exponential. So it goes like an exponential of e to the s naught. So that's why this piece is doubly non-perturbative in 1 over g Newton. So let's see what gets a bit more intuition, or what this rho correlator actually looks like. So, the big contribution in terms of scale on the y-axis comes from the disconnected piece. And if you expand the disk here, E bar is just E plus E prime over 2. And I'll just denote delta E as E minus E prime. So I'll plot this plot as a function of delta E, keeping E bar fixed. So at leading order, the disconnected piece that I'll show in blue is just a quadratic function, which starts out at a scale that goes like e to the 2s naught, right? Each of these rho zeros goes like an e to the s naught. Then there's a wormhole correction that's order 1, but it becomes very important once I go to small energy differences. And this is supposed to capture the relatively large scale structure of how eigenvalues are distributed. So this corrects this piece. The wormhole piece corrects the plot to be divergent as delta E 0. So naively, that's a bit counterintuitive, but because what's famous about random matrix theory is eigenvalue repulsion. So how come the wormhole, pushes delta E, pushes the density of state correlator to diverge as the energies become the same? Well, this is resolved by the next piece, which is the doubly non-perturbative piece, which I'll plot in red. Purple, which essentially gives very large oscillations as I approach delta E goes to 0, and essentially makes the density correlator go to 0 as the energy difference goes to 0. So essentially, one important thing to notice is that if I take delta E goes to 0, this plot, this pole actually cancels with this pole. And the order 1 piece of that remains from the delta E expansion when delta E goes to 0, coming from the cosine, actually cancels this disconnected piece. So that's why this density correlator goes to 0 as delta E goes to 0. And the physical meaning of that, these oscillations are spaced like e to the minus s naught, right? Because of this factor of rho 0. The physical meaning of this is that if I fix an eigenvalue of the matrix to be somewhere, it's impossible to find another or it's very unlikely to find any other eigenvalue that's infinitesimally close to it. I have to go at least e to the minus s naught away, order e to the minus s naught away to find another eigenvalue of the matrix. So this is what this plot means. And now, to compute the spectral form factor, yesterday we computed the spectral form factor only including this term and this term. And we saw that this was the decaying term, right? This was the disk contribution. And we saw that this contribution that corresponded to the wormhole, this was the thing that gave square root of beta 1, beta 2 over beta 1 plus beta 2, gave a ramp. But what happens if we also include these doubly non-perturbative terms? Well,
What happens with the delta function? You said that basically
so the delta function is a delta function here, and the meaning is somewhat obvious, which is that if I set an eigenvalue to have energy E, I of course will find another eigenvalue there if I set E prime equal to E, because I already forced an eigenvalue to exist at an energy E, right?
the prefactor is e to the power 2s. That's an artifact of what you do?
No, it's a power of E to the S.
Sorry, s, yeah. Is that an artifact of what you're doing, or is what's the meaning of this? I thought you would get just one. Or why is the prefactor e to the power of s essentially?
Good. It's because let's imagine that I integrate this over some interval, integrate E and E prime over some interval that scales, energy intervals that scale like e to the minus s naught. On average, I will find one eigenvalue in that interval. So that's precisely what this factor of rho 0 of E.
It's sort of like a normalization that in your spacing of sort of like your ignorance of how much energy you have is essentially you have one.
Yeah, yeah. Okay.
How did you compute this?
I didn't compute it. One uses the non-perturbative corrections in the matrix integral. You can compute it by, instead of inserting resolvents in the matrix integral, insert determinants. And using these determinants, you end up finding new saddles that end up giving you these types of corrections. I can send you a reference if you want. Okay. The problem is that this doubly non-perturbative term doesn't have a geometric meaning, right? Because the only things that we associated a geometric meaning to were things that had genus, and a thing that has genus contributes e to the minus s naught times the Euler characteristic. Here, this term doesn't fit in that expansion. It's like a resummation of literally all the surfaces that I'm talking about.
Even from that point of view, it's still a little confusing because you might say, suppose I want to do that and expand it. Excessive powers of e to the minus s naught. It's not in a form which is mutable. Cosine.
Yeah.
There's no. Not going to expand a small argument. If you take e to the s naught large, you have a cosine large argument. This isn't a manifest expansion. Powers of
no, definitely it's not a manifest expansion. Yeah, that's why it's a doubly non-perturbative term, right?
But it's also just not manifestly a resummation of those sort of small types of terms.
Yes.
And power scaling did not.
How scaling is related to this to these cosines. Essentially, your argument from yesterday was that the cosine can be viewed as a resummation of the power series that came from the leading term in the polynomial associated to each volume. So imagine that you took the volume is a polynomial, but you just dropped all the terms in the polynomial except for the one that had the largest powers in B. Then essentially you get in the spectral form factor you get an expansion in T, the spectral form factor time, and that expansion precisely agrees with what you get from this doubly non-perturbative correction. So in some sense, that's why I was saying that this cosine can be viewed as a resummation of all the terms.
Focusing on this term relied on the fact that JT gravity was one loop exact, right?
On which term?
Well, so first of all, having looking at the genus expansion,
Yes.
already relied on
Yes.
JT gravity
Yes.
being one loop exact.
Precisely.
This is even more exponentially tiny.
Yes.
So, is there some general lesson I'm supposed to extract from this, which would apply to any gravity theory, or is this really special to something that's just topological and has no other crap in it?
Well, I would say that the general lesson comes precisely from this correlator of rho of V prime, which is believed to be universal, even in theories that are not one loop exact. So, for instance, some people believe, I don't think it's proven by any means, that if you take n equal 4 super Mills, let's say, and compute its partition function, compute the spectral form factor, let's say, and extract from that this rho of V prime correlator for very large energies E. We can still talk about the statistics of eigenenergy repulsion, even in n equal 4 Sprague Mills. They believe that you would still get this plot, even though the partition function of n equal 4 Sprague Mills is not one loop exact in n. It has probably an asymptotic series in n. There is non-perturbative corrections in n, and also doubly non-perturbative corrections in n, and many other things. But this eigenvalue repulsion is believed to be a universal feature.
Yeah, that's universality of chaos.
Yeah, it's some universality of chaos, but in this model, in this gravitational model, it's in some sense clear where it comes from. It comes from the sum over all possible bulk geometries. The question, the open question was not to resolve things from the boundary perspective. There, okay, if we assume that the model is chaotic, we know everything. The question was, how do we see these features from the bulk perspective? And these models gives us some intuition that perhaps these sum over non-perturbative corrections could start building up to proving that these black hole microstates, this is what these are at the end of the day, are obey chaotic statistics.
Right, but yeah, so yes, and I think maybe that's the heart of the question I asked. So from the boundary perspective, we understand perfectly well that n equals 4 Mills has energy eigenvalues, and they're repulsive because high spectrum it's chaotic and blah blah blah. So here you reproduce some of those features by first doing some topological expansion, adding handles, wormhole geometries, and so on and so forth. So the first question I probably should have asked is, should I believe that bulk ADS5 cross S5 geometries that I should be thinking about some kind of 10-dimensional Euclidean wormholes as meaning anything? Mm-hmm. And then the second question would be, is there going to be any kind of bulk calculation that I could do to see the eigenvalue repulsion, which is obvious in the dual theory.
Good. So let me start by answering the first question. I would guess that the wormhole that you would find in 10 dimensions would at most give you some information about the statistics that these eigenvalues satisfy. Not necessarily about not necessarily about the fact that this model has a factorization problem or anything like that. It's just that even n equal 4 Sprague-Mills has statistics for the scaling dimensions when the scaling dimensions are large. Like suppose that I could solve the theory exactly on a computer. I diagonalize the Hamiltonian, I get all the deltas. I could still draw this plot, right, as a histogram. The question is, and okay, this is a conjecture, but perhaps the belief is that the plot that the histogram that you would get for certain quantities that are so-called self-averaging, meaning that they're insensitive to the way in which I choose what energies to keep and what energies to throw out, or things like that. The belief is that the things that are self-averaging might be captured by wormhole effects even in the higher dimensional bulk, or at least that is my belief. I don't think that implies that the theory is not factorizing in any way. I just think it's a statement about the gravitational path integral being smart enough to not only capture the what's at the end of the day the statistics of the partition function itself, the average partition function, right? In some sense, the gravitational path integral, we know it's smart enough to capture some sort of coarse-grained version of rho of E, but perhaps it's also smart enough to capture coarse-grained versions of rho of E prime. Okay, so I think that was your first question. Your second question was whether the sum over geometries in higher dimensions can tell you anything about eigenvalue repulsion. And I guess it depends what you mean by eigenvalue repulsion. If eigenvalue repulsion, you mean only this doubly non-perturbative term and not also this universal piece that kind of gives you the structure of how nearby eigenvalues are spaced out, then I think reproducing this doubly non-perturbative piece might be difficult since we don't know how to do it even in the 2D model, even in the toy model. But reproducing this part, I think, is doable, perhaps. If we understand better what sort of gravitational contributions we really need to include when studying this statistical object. Does that answer your question? Well, let me also put it this way. I'm not sure there is anyone that could give you a satisfying answer to your question. Yes.
That's almost a question. I just want to lift up. In some sense, there's a choice of the original potential in the matrix model, which then was reflected in the density of states of energy.
Yes.
Then leads to this cosine function. If you mess with the choices you made with the potential, and then what happens to this cosine? Is it in any sense universal, or is it? I mean, obviously, it's got to cancel the pole at the. But what else? No. If I start messing with the input data in terms of the potential, what happens to this discussion?
We change rho of E.
Yeah.
You just change rho of E, and if you do this plot,
yeah, exactly. Change the rho of E. I see. It doesn't change.
It doesn't change the plot because.
Thank you.
Because this plot is at fixed. Yeah. So it's at keeping E bar fixed.
Thank you.
So rho 0 of E bar is just some number for the purposes of this plot.
It doesn't change this plot.
But it doesn't change the shape of the correlator. It just changes the scaling, the exact spacing of oscillations, and so on. But the shape is universal. Okay. Well, go ahead.
Sorry, really quick. I wanted to ask, going back to this question of Why do you say that the cosine terms comes from a summation, like this sum over all genus? Like, I mean, as far as I understand, the only paper in which that possibility is kind of said is the tau scaling limit papers. Before that, there's even purely in random matrix theory, there's no known way to like resum topological recursion to get.
Yeah. I meant morally. I didn't mean like
Okay.
anyone didn't explicit. The explicit computation involves inserting other operators that can be used, like these determinants, that can be used to deduce this presence of the sign kernel in the row correlator. But even in the row correlator, there is an asymptotic series in e to the s naught. And okay, the question is how you resum it. Any other questions? All right, so perhaps let me end with a final plot and then a discussion. So the final plot that I'm going to make is again one of the plots that we started out on our first day, namely the full calculation of the spectral form factor. So we saw that it was decaying with a power of t cubed from the disconnected piece. Yesterday we deduced the ramp. And now we also have this additional doubly non-perturbative piece that, yes, should be viewed as coming from a resummation of all genus. And the fact that this guy, when I resum this guy plus this guy, I have no pole in E minus E prime, means that at very late times, the Fourier transform with respect to E minus E prime has no time dependence. The only scale, the height of the Fourier transform of very late time is just given by this contact term, which is e to the s naught suppressed compared to where the spectral form factor started out at e to the 2s naught. So essentially, at e to the s naught past e to the s naught, what happens is that the Fourier transform of this cosine ends up giving you a factor of minus t, which precisely cancels the growth from the ramp. And what you end up with is a plateau that you see at time at a value that starts at e to the s naught, and a time that starts that whose value is m break inverse times e to the s naught. So this is exactly what you would expect to see from the boundary side, where now this part of the plot was derived from gravity alone, and this part of the plot was derived from assuming that the asymptotic series that you find in the gravitational path integral ends up agreeing, ends up giving you doubly non-perturbative corrections that agree with those obtained from the matrix integral that has the same asymptotic expansion. Namely that in JT gravity, you will also find these this cosine term. Great. And perhaps I should mention that two other consequences of this rho of E prime correlator are the following. I unfortunately don't have time to go through the derivation, but it turns out that one can show that the 2-point function, so yesterday we derived the 2-point function on a disk. One can, in principle, derive the 2-point function on an arbitrary genus surface. And if you resum the 2-point function on this arbitrary genus surfaces, you will find that it satisfies the same type of decay, growth, and plateau. So in some sense, this in this toy model, this resolves the version of the black hole information paradox that was formulated by Juan for eternal black holes. But I should emphasize, this is a toy model. toy model. And the second thing that I should mention is that from the 2-point function, one can also give a definition for the length of the bridge that connects the left and right side of an eternal black hole in these two-dimensional models. So one can also deduce how the length of the black hole interior behaves with time. And one finds that there's a different cancellation that's less discussed in the random matrix literature that leads to a plateau. So the shape that you'll find for the expectation value of the length with time by using this formula is that the length grows linearly with time, after which it plateaus at the time that goes like e to the s naught, and the value that goes like e to the s naught. And here, the important thing is that while the disconnected piece was completely unimportant at late times for the spectral form factor, it becomes very important for this length at late times. So in some sense, the length at late times is a much better probe of the eigenvalue repulsion itself. Namely of the fact that this rho of V prime correlator goes to 0 as delta E goes to 0. That wasn't that important for the spectral form factor. For the spectral form factor, one actually only used that it goes to a constant at late times. Sorry, yeah, that this rho of V prime correlator goes to a constant as delta E goes to 0.
So how much of this was already baked in by just the fact that you had a matrix model and finite spacing of eigenvalue?
I would say not at all, because the connection between 2-point functions in gravity and objects in the matrix model was not at all obvious. So essentially, you use a geometric derivation for what the 2-point function is as a function of eigenenergies to say what O left, O right is in this case. So in some sense, I find that I find these two observations even more interesting than the observation for the spectral form factor, because, okay, once you know that the GT gravity is dual to a matrix integral, then you know what the spectral form factor of a matrix integral looks like, which is this shape. While if I tell you, oh, deduce the 2-point function in gravity from the matrix integral perspective, you first have to compute what ingredients relate, what's the map between the 2-point function and eigenvalues in the matrix integral. And that's somewhat non-trivial. And the same for the length.
Do you need? You need the operator elements. Like
You need the operator element, yeah.
So then for just that, you just use ETH, right? In the paper, are you referring to the paper by SAD, like the baby universes, ETH, and so on?
Yes, but these operator elements have an explicit formula that's not dictated by ETH. Namely, the formula that I wrote yesterday for what OE prime is, as you know, that product of gamma functions has no connection to ETH. It just has an independent geometric derivation in the bulk, right?
Okay. And so you don't need to use ETH, you can just use that.
Yes, yes. Okay. Well, okay, the question then is, does that formula hold at higher genus and so on? So you have to rederive that formula at higher genus, and unfortunately I didn't have time to show you, but the derivation of how the 2-point function behaves, the boundary to boundary 2-point function behaves like, is very cute, because it relies again on an exchange between the sum over geodesics on the geometry, the boundary to boundary geodesics this time, and the quotient by the mapping class group. Good. So for the last 5 minutes, let me make a few comments. So I already responded. One of the comments was already part of my response to Emil's question. Namely that the quantities that are in some sense most interesting are self-averaging quantities. So these are observables x, for which x squared minus expectation value of x squared in the ensemble is much smaller than expectation value of x. And the reason why these are very interesting is because even if we choose a single member of the ensemble, even if we just drew one Hamiltonian at random from our ensemble and computed a certain the expectation value of x in that member, it's an extremely high likelihood that the expectation value of x in a single member of the ensemble will reproduce the expectation value of x that we computed in the ensemble average. So if we believe that wormholes have anything to do with statistics in higher dimensions, statistics of things in higher dimensions, we should care about, and we also believe that in higher dimensions, we can't really talk about ensembles of, of theories necessarily. Then what we should really be looking for are the quantities that are self-averaging, for which computing things in an ensemble could serve like a crutch to simplify some computations. The second comment is about wormholes in supersymmetry. So here we saw that the role that wormhole played, was connected to capturing chaotic behavior for the spectrum of the theory. But in supersymmetric theory, some of the states are special, namely the BPS states. Those are the lowest energy states in a given charge sector. And this fact is also captured by a gravitational computation, which shows that if either if I send beta to infinity, or if I keep beta fixed, but fix Euclidean angular velocity to be 2 pi over beta, so this guy computes a degeneracy, this guy computes a connected part of a degeneracy, this guy computes a connected part of an index. So they would capture the variance of these quantities between different members of the ensemble. Both quantities, path integrals end up giving 0, not only for these wormhole geometries, but also for wormhole geometries that have arbitrary genus.
What is the matrix model?
So it's not actually known what the matrix models are for super JT gravity with more than n equal 1. And n equal 1 does not have BPS states. I think there is a paper of Turiachi and Witten that will come out the next 2 weeks that will write down a matrix integral for the n equal 2 super JT gravity. Okay, and another final observation, another final comment, is that supersymmetric wormholes, we might naively think that this means that, okay, BPS states are boring from this perspective, or maybe you take the opposite point of view, that BPS states are under control from this perspective. I take both points of view. The other comment that's worthwhile is that supersymmetric wormholes with matter propagating between the two sides of the wormhole. So if you compute the wormhole with infinite Euclidean boundary length for an arbitrary operator insertion O, this guy is non-vanishing, even though these guys vanish. And this guy, this property can be exploited for a different count of BPS states that more reproduces the type of counts that people try to do in non-supersymmetric cases. So in some sense, this captures the fact that while the BPS, the number of BPS states doesn't have non-trivial statistics, the expectation value of some arbitrary operator in a BPS state has non-trivial statistics.
Version of the statement that OPE coefficients like that, or
Yeah, it should be a statistical statement about OPE coefficients.
I mean, you know that you have two BPS and a third non-BPS. Those general are functions of the coupler. This is reflecting that. Is that right?
Perhaps, yes. Okay. So finally, some open questions. Well, one open question is if we believe these wormholes exist in higher dimensions and contribute to a multi-boundary partition function, how should we interpret the lack of factorization? And as I mentioned, the point of view that I would advocate for, is that these wormholes are only useful for capturing statistics, but there's not necessarily a factorization puzzle when you include all possible corrections in the bulk that we don't have any control over. The second thing is, how do we go from these toy models of non-perturbative corrections to the real thing? And I think perhaps BPS states provide a nice bridge between the two, because they're on the one hand more under control in their count, but they still have non-trivial statistics for some of the other observables. So the third question is, can we find UV complete theories in the greater than 2 dimensions that have bulk duals and are ensemble averages? And a final question that I think is solvable even in this toy model, but has not yet been fully addressed or fully explored, is what is the experience of an inflowing observer? Even in this toy model, I think that we just discussed, with topology changing processes, one can try to formulate this question in a diff invariant manner and try to find an answer. Okay, and perhaps that answer will help us give some intuition about what happens for higher dimensional black holes in ADS, at least. Okay, so that was it. Thank you very much. Yeah.
What do you mean by the third point? Like UV complete boundary theories, like a CFT, you mean, be greater than 2?
Yeah, like are there good ensemble averages over CFTs that have an independent definition of a bulk dual.
There is, right? I mean, you can average n equals 4 super Young mills over the conformal.
Yeah, but it doesn't have an independent good definition of the bulk. It's well, it's just okay. Like the answer is that the bulk is an average over bulks.
The bulk is simply the supergravity theory.
Don't think that was proven. I would say that the bulk is an average over whatever type 2b, different type 2b string theories in the bulk. That doesn't mean that the bulk is the supergravity theory. Namely, you can average n equal 4 super Young mills, but the wormhole distribution that you naively get in supergravity when you average over the conformal manifold of n equal 4 super Young mills plays no role in that average. It doesn't capture, at least as far as I know, it doesn't correctly capture the statistics of anything related to that average. Let me give you an example. So I think the derivation that one has for the fact that the index factorizes in these theories also applies to other observables that are predicted by supersymmetry. And there are observables that are predicted by supersymmetry that explicitly depend on the coupling of n equal 4 super Young mills, right? Like expectation value of Wilson loops on S4. So somehow when you average over the conformal manifold, that tells you that that expectation value has a non-trivial variance when you do an ensemble average. But from the bulk perspective, you will not be able to recover that non-trivial variance. So that's why I would say that we do not have yet an example where ensemble averaging does anything useful in higher dimensions with regards to the bulk, a definition of the bulk, providing a different definition of the bulk.
Yeah. These things are compatible. If you're looking, when you say independent bulk definition, you mean something besides an average over bulks that are microscopically defined.
Something besides an average over bulks, yeah.
Situation where you take large n and that average localized onto supergravity, it's just a feature of that average over bulks, and that's fine. But it's not what you're looking for, in that you want to just define the bulk theory kind of independently of some UV complete microscopic string theory description in a way that is dual to the ensemble and not in this trivial way where the average of both sides maps to each other.
Exactly. Like somehow we'd like an ensemble average of different string couplings or something like that, perhaps to tell you that, oh, somehow wormholes become important when you take this type of average, but we don't have that example yet. Any other questions?
Maybe if you have time, we should save them for lunch.
Great. Well.
Thank you again for a great course.